Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zone. So we continue the chapter magnetism and magnetic material, and our topic today is the dipole in a uniform magnetic field. So we have given a uniform magnetic field in which we place a magnetic dipole, or you can say a simple bar magnet that is behave like a magnetic dipole. So first derivation is torque on a bar magnet in a uniform magnetic field. When we place a bar magnet in a uniform magnetic field, then what happens? Try to understand. Like this is the uniform magnetic field. In uniform magnetic field, lines of forces are parallel to each other, and intensity in uniform magnetic field is constant everywhere. Okay, so this B magnetic field is uniform. Uniform means same direction, same magnitude. Two things are there. Uniform means same direction and same magnitude. Clear? So two things are same. One is magnitude and direction. Then the field is said to be uniform magnetic field. Now see, this is the bar magnet. Okay. Now if you have a field magnetic field B, then we have the definition magnetic field intensity is equals to force per unit test pole. Nitin, do you know this formula? We already have derived this. B equals to F by M. Yes or no? In the first chapter, first class, okay? First lecture, we have completed this. So force can be written as M into B. Agree? So F vector equals to M into B vector, where M is the pole strength, right? So look here. Here two poles are there. Suppose this is north pole, having pole strength M. So the force, magnetic force, will working towards here in this direction. That is equals to MB. Clear? And this is south pole. So by nature, the direction of force will be in opposite direction to the field, but having the same magnitude, MB. Clear? So you see, there are two equal and opposite forces, okay, acting upon this magnet. So certainly this magnet will revolve in this direction. Understood? Clockwise direction. Why? Because a torque will be produced because equal and opposite forces are acting in different directions. Clear or not clear? Now one more thing. This is the direction of magnetic field, and this is the direction of dipole moment, magnetic dipole moment, because the direction of magnetic dipole moment is from south pole to north pole. So here is the angle theta. This is the angle theta. Clear? So theta is the angle between direction of magnetic field and magnetic dipole moment. This angle is theta. Clear, beta? Magnetic dipole moment and magnetic field intensity or magnetic field. Clear? So we have to calculate the amount of torque working upon is this dipole. Okay, as equal and opposite forces are acting there. So what amount of torque will be produced here on a magnet? Clear? So by the class 11th formula, if two forces, this is called lever arm, upon which the two forces are act. This is called lever arm. Clear? Lever arm. Yeah, lever arm. Okay, upon which two forces are acting. Like when you pedal in a cycle, yes, cycle, two pedals are there. One is here and one is here, and you rotating continuously this pedal. Yes or no? Your upper foot is like here, and this one. Understood? So they will produce a torque, and this pedal, this whole lever will rotate like this. Here two forces are acting. So this is force F, same amount of force F equal to mb and F equal to mb. Clear, beta? Now the formula for amount of torque generated, this is equals to torque is equal to force multiplied by perpendicular distance between the two forces. This is the formula from class 11. Must remember this formula. Perpendicular distance between the two forces. Understood? So perpendicular distance between the two forces. Then how will you get the perpendicular distance between the two forces? Look, this is the one force, this is the another force. Okay, beta? So perpendicular force, make this for extend and draw a perpendicular. This distance, this one, x, suppose this is x. This distance is the perpendicular forces between the two distance. Okay? Because one force is going here, another one is this. So this is definitely the perpendicular distance between the two forces, and we have to calculate this one. Clear, beta? Now see how, in what way you can calculate this. This angle is what? Theta. Why? Because this is capital M and this is the direction of magnetic field B. Okay. Yes. So if this angle is theta, then by the rule of corresponding angle, this angle is also theta. Clear? Corresponding angle theory, this theta. So this is also theta, right? Now apply sine theta in this triangle. Sine theta equals to perpendicular upon hypotenuse. So for the sine theta equal to perpendicular. For this angle theta, perpendicular is the opposite face. So this is x. Yes or no? And hypotenuse is the longest arm of the triangle. So this along which your magnetic dipole is going, the length of this arm is equals to 2L. Yes or no? See here. This is what? This is magnetic length. Supposed to be 2L. Clear? Okay. So this is equals to 2L. So x divided by 2L. Clear? So x equals to 2L sine theta. X equal to 2L sine theta. Clear? So from here, x equals to 2L sine theta. Now place the value here in the formula of torque. Torque is equals to force. What is the amount of force, beta? mb. And distance you have calculated mb multiplied by 2L sine theta. Right? So torque is equals to perpendicular distance between the two forces. We just have calculated the value of perpendicular distance between the two forces as x. Okay. So the torque F cross x. Clear? So in the place of F there is mb and in the place of x there is 2L sine theta. Clear? Now separate m into 2L as together and b sine theta. Clear, beta? So this becomes m into 2L. Okay, in first lecture we have seen that m equals to magnetic dipole moment, that is equals to pole strength multiplied by effective length of the magnet. So can you write here capital M? So mb sine theta, right? Done. So this is the torque. Now vector form. So might you know A cross B equals to mod of A mod of B sine theta dot n cap. Clear? So if you replace in vector form, so torque is called axial vector. So axial vector is directed anti-clockwise or clockwise. So direction is goes along the axis by right hand thumb rule. So see here, torque equals to in vector form mb sine theta mb sine theta, and direction is perpendicular to the plane given by n cap, right? So torque equals to, now eliminate this sine theta by using this formula. So if you look this formula in a reverse way, in back way, so A cross B, it can be written as M cross B. Clear? So MB sine theta may be written as M cross B. Okay, so this is what, this is vector form. Clear हो गया? Yes, so torque is equals to MB sine theta. This is very important derivation. Now, two special cases we have. First, minimum torque. For torque minimum, for minimum torque, theta equals to 0 degree. So torque equals to MB sine 0. And this will give you 0 because the value of sine 0 equal to 0. So making it 0, right? For torque maximum, sine theta should be maximum. So sine theta will be maximum at sine theta equals to 90 degree. So torque equals to capital M, capital B, sine 90, that is equals to M into B. Clear, beta? So this is the condition for maximum torque and minimum torque. Clear? So yes. So let us see the systematic derivation here. All the things. Yes, beta? Yes, first you see this, after then you write, please. Okay, so here is the angle theta. So in the same way, this angle is also theta. So this length is 2L. So considering x by the formula, it is become 2L sine theta. Now reading the theory, let a bar magnet be held at an angle theta to a uniform magnetic field B. 2L be the magnetic length of the magnet and small m be the strength of the each pole. Let 2L be the magnetic length of the magnet and B and small m be the pole strength of the each pole. Then force on the north pole is equals to mb, because north pole is positive equivalent, so it will in direction of force in the direction of magnetic field. But south pole is negatively equivalent, so that force will be in opposite direction of the north pole, right? So force will acting in the opposite direction of B. So here these two forces being equal and opposite and having different line of action. Remember, this line is very important. Torque is acting only when the line of action are different, having different line of action. Look here, like there is a lever like this, and you have two forces having same line of action. This is MB, this is MB. Okay, you see, this is the same line of action of these both the T forces, two forces. So torque here will be 0. Clear? But here the line of action of two forces are different. Yes, this is the lever arm. Now, one force is acting towards here and another force is acting towards here. So they having different line of action. The upper one force have this one line of action, and the downward force having this one line of action. Clear? So they both having different line of action. So torque will act only when the forces having different line of action. So here it is. So constitute a couple. When two forces are acting simultaneously, okay, and they produce a torque, so they are called to constitute a couple, right? So the couple tends to rotate a magnet so as to align in the direction of B vector. Yes, this couple of forces try to align this magnet in the direction of field. Means they try to rotate this dipole. Yes or no? They try to rotate this dipole and try to align this dipole in the direction of this field, right? When the this magnetic dipole came in the direction of magnetic field, this is called stable equilibrium. Okay, see here, when dipole try to rotate this magnet in the direction of magnetic field, and once the magnet comes in the direction of magnetic field, okay, so the magnetic field and magnetic moment get aligned, and theta equals to 0 degree, then amount of torque equal to 0. This situation is called stable equilibrium. What it is called? Stable equilibrium, yes. Okay. So This couple tends to rotate the magnet so as to align it along B vector. So torque on a magnet is given by force multiplied by perpendicular distance. So force in each case it is mb, and perpendicular distance here is NA. Right, beta? This is perpendicular distance NA. So MB multiply NA. More correctly, you can write it perpendicular distance between two forces. Yeah. So MNA becomes 2L sine theta by trigonometry. Now combine M and 2L. So it will become capital M equals to M into 2L. Okay. MB sine theta. Now MB sine theta in vector notation, you can write M cross B. For maximum torque, theta is equals to 90 degree. So torque, maximum torque, the magnitude of maximum torque can be given as MB. And for minimum torque, theta equal to 0 degree and theta equal to 0 degree, on theta equal to 0 degree, the torque will be produced as 0 or no torque will be produced. Clear? Yes. So this is the complete derivation. Now write it. Next concept is potential energy of a magnetic dipole in a uniform magnetic field. Okay. So potential energy, before obtaining the potential energy, we would go to calculate work done to rotate a dipole. So our first derivation is work done to rotate the dipole. Clear? Work done to rotate a dipole from theta 1 to theta 2. Theta 1 is the any random angle that our dipole is making with the magnetic field, and we bring this dipole up to angle theta 2, another random angle. Clear? So what is the formula for work done in mechanics? There is a slight difference because this derivation comes under rotational dynamics because you're rotating the dipole here. So first try to understand the concept of class 11th. dW is equals to F dot ds, right? This was the work in mechanics. Clear, beta? dW equals to F dot dx. And somewhere it is also written as F vector dot dx vector. That is also fine. Clear, beta? Now this is dW. So W is complete work is given by integration of dW, and work done is equals to integration of F dot dx. This is the class 11th concept. Clear? Now, in the case of rotational dynamics, this is for mechanics, okay, or linear dynamics. But in the case of rotational dynamics or rotational mechanics, situation is somehow changed, and there dW, which factor is responsible for rotation? Force? No. Torque is rotated. Torque is responsible. So the formula becomes dW is equals to T dot d theta. Clear, beta? In the place of force, there is torque, and in the place of displacement, linear displacement, there is angular displacement, that is d theta. So work done is equals to integration of T dot d theta. Clear? Hmm. So now this is the main important result that will help us to calculate the work done, okay, to rotate a dipole in a magnetic field. And we have the situation is like this. This is our magnetic dipole. Initial this magnetic dipole, this is direction of magnetic field B, and this is the direction of magnetic moment M. This magnetic moment is making an angle. Suppose it is theta 1, right, beta? And you rotate this dipole and bring in a new position like this. Yes, anti-clockwise. Work in direction anti-clockwise taken as positive, and you bring up to here in theta 2 angle. Understood? Initially is what? Making an angle theta 1, and then you have rotated it, and the final angle is theta 2. Clear, beta? So now amount of work done. So first you will write the derivation for dw is equals to torque into d theta. What we have as a torque? We just have calculated dw is equals to torque. You know, torque is equals to mb sine theta. mb sine theta. We just derived this formula, torque equal to mb sine theta. Yes or no? Okay. So torque equals to mb sine theta. Now dw equals to mb sine theta into d theta. Clear? Now complete work W is given by integration of dW as we continuously rotate this one from theta 1 to theta 2. So place the value of here dW, that is equals to mb sine theta and d theta, and the limit of theta varying up to theta 1 to theta 2. Clear? Hello? The limit of theta is going from theta 1 to theta 2, initial to final, right? So this is W. Now solve this integration. W is equals to m is the constant, b is constant. Inside the integration sign, there is sine theta, d theta. Limit is theta 1 to theta 2. Clear? So W is equals to mb. Now integration of sine theta is equals to minus cos theta. Clear? Do you know the integration of sine theta is equal to minus cos theta? So integration of sine theta equals to minus cos theta, and limit is theta 1 to theta 2. So W is equals to negative of mb, minus sign can be taken out, and here cos theta, and limit is from theta 1 to theta 2. Now place the value here. So it will become W is equals to minus mb, upper limit, cos theta 2 minus cos theta 1. Clear? Okay, so W is equals to minus mb, what we have written, cos theta 2 minus cos theta 1. Dissolve the minus sign, take it inside, then it will become W equals to mb cos theta 1 minus cos theta 2. So this is the derivation for work done to rotate a dipole. Clear? Okay. So let's see the derivation for potential energy of a magnetic dipole. But before potential, this is not the potential energy. This is first work done. After then we will calculate the potential energy. Let us calculate potential energy right here. Okay, potential energy. What does it mean for potential energy? In physics, we have considered a standard direction of the dipole, that is theta is equals to 90 degree. Here, like magnetic field is going here, and this is the direction of magnetic dipole. So here theta is equals to 90 degree. Okay. So this is the standard position of the dipole. And when you rotate from this position to any another position, like this angle is theta, second angle. So your initial angle was 90 degree, theta 1 is equals to 90 degree. That is a standard situation, right? Standard situation. To theta 2 is equals to theta. So work done, amount of work done to rotate from perpendicular situation theta equals to 90 degree to at any angle theta, the amount of work needed to perform this work is called potential energy, and this energy is denoted as U, right? So in case of this, W becomes U because U is the standard symbol for potential energy. So U is equals to, we have seen MB sine theta 1 minus sine theta 2. Sorry, cos theta 1 minus cos theta 2. Okay, MB cos theta 1 minus cos theta 2. So MB, place the value of theta now. What is theta 1? 90 degree because initial angle was 90 degree. Okay, so this is 90 degree minus second angle is any of the end angle cos theta. Okay, so MB in bracket cos 90 equal to 0 minus cos theta. So it will become minus MB cos theta. This is called potential energy of the dipole, right? So this is equals to minus mb cos theta. Clear? In this is potential energy is the scalar quantity. So you can write using dot product. How? You know A dot B equals to mod of A mod of B cos theta. So if you're going right to left, then you can reversing the action here. U equals to negative mb cos theta may be written as vector m dot vector b, right? Because a b cos theta may be written as a dot b. So in the same approach, mb cos theta may be written as m dot b, negative of m dot b. Clear? So this is the formula for energy. Yes, energy is stored in a dipole. Okay, or potential energy of the dipole. Yes, so reading this potential energy of the magnetic dipole in a uniform magnetic field. So first we are going to derive the total energy, the total work done. Consider a magnetic dipole m vector held at an angle theta to the direction of the uniform magnetic field B. Then a torque acting on the dipole at torque equal to mb sine theta. Yes. If the dipole is rotated by a very small angle d theta against this torque, then a small amount of work done. We have to apply the same torque against the working torque. So if the working torque equal to mb sine theta in clockwise direction, we have to apply the same torque in the anti-clockwise direction. dw is equals to torque dot d theta. This is the work done by anti-clockwise torque. So torque is equals to mb sine theta d theta. dw equal to mb sine theta d theta. Clear? Now work done. So integrate this one from in the limit theta 1 to theta 2 becomes the same formula. Torque equals to minus mb cos theta 2 minus cos theta 1. You can dissolve the negative sign as I have done it before. So it will become mb cos theta 1 positive minus cos theta 2 negative. Clear? Now for theta equals to 90 degree, and this is the derivation for potential energy. So this is from here, it is for potential energy. Suppose theta 1 is equals to 90 degree, standard situation, it is called standard situation or reference situation, and theta 2 equals equal to theta, any random angle. So you will have w is equals to mb cos theta. This is the work stored in the dipole in the form of potential energy. Clear? So this is called U is equals to minus mb cos theta. In dot product it is equal to minus m dot b. Okay, now note it. Okay, coming to the next derivation, magnetism and Gauss law. So first our next topic is, right, Gauss law of magnetism. Very important. Gauss's law of magnetism. Gauss's law of magnetism. What we have learned in electrostatics, you know, in electrostatics, there is an imaginary surface that is called Gaussian surface, and some charges are there, q1, q2, like this. And from these charges, if they are uh, positive charge, then they radiate outside some electric lines of forces. The lines of forces passing perpendicular to the surface are called electric flux in that chapter, right? So according to the Gauss law, you know, amount of total flux is equals to what? The total amount of flux equals to Q by epsilon naught. Q enclosed, the total charge enclosed in that surface. Okay, Q enclosed by epsilon naught. This was Gauss law of electrostatics. But now we studying here magnetism. Okay, and the value of electric flux is also given by phi E is equals to closed integration, bounded integration of electric field over a closed surface E dot ds. This was flux, okay, total flux, and it is given by Q by epsilon naught. So this is complete Gauss law. This is completed Gauss law. Phi net flux, electric flux is equals to E dot ds. This is equals to Q by epsilon naught. Now, we are discussing here the Gauss law for magnetism. So in electric case, we saw that electric flux phi E. So this was phi E, electric flux phi E through a closed surface. That closed surface was called Gaussian surface. Okay, a imaginary surface that is symmetric about the charge distribution was called Gaussian surface is equal to the total net charge Q enclosed by the surface divided by epsilon naught. Yes. So this was the definition of Gauss law, that total electric flux phi E is equals to 1 by epsilon multiplied of the charge enclosed. Now, the situation is radically different from magnetic field, which are continuous and form closed loops. So here the situation is radically different. I mean to say, Gaussian surface 1 and 2 in figure A and B. Now see here, we are taking here two Gaussian surface. Look here, this is the first Gaussian surface given as, sorry, this one is second, and first one is here. This is Gaussian surface, okay? And this is the case of a magnet. So here it is a magnet. Another bar magnet is given here. Oh, this is the magnetic axis along the north-south pole. Okay, this is magnetic axis, and this is our Gaussian surface. Now, what we have to understand here, Gaussian surface 1 and 2 in figure A and B. In figure A and B, the number of magnetic lines leaving the surface are balanced by number of lines entering it. Now see here in this diagram, as the number of lines are entering in the surface, exactly the same number of line going out from the surface. Yes or no? Yes. The same number of line entering to the surface, exactly equal same number of line exiting from the surface. See here, this is the one of the flux. Now this is entering and the same flux is leaving from the surface. Clear or not clear? Why? Because the reason behind this is electric lines of forces like isolate charge, that is called unipole, like plus q is can exist, and it is unipole, and unipole emitting the electric lines of forces. Okay, there is no need that these lines of forces come back inside this surface, but whenever there is a magnetic lines of forces, whenever there is a magnetic lines of forces, so from north to south, emerging from north to south, and came back from south to north, right? So they are forming a closed loop. So if there is a loop, see here, from this one, the lines of forces are going out of the out of the this loop, and again they entering to the same loop. Yes or no? Okay, so see here, this is a loop placed in a 3D. So if this line is entering, so the entering flux and this is outgoing flux. Outgoing flux is always taken as positive and entering flux is always taken as negative. So total flux will cancel each out and net flux is given as 0. Clear? So total amount of magnetic flux equals to 0. So Gaussian surface 1 and 2 in figure A and B, same number of magnetic lines of forces leaving the surface balanced by number of lines of forces entering it. Just count here. Nitin, see this is a Gaussian surface. I am making this Gaussian surface in red color. Okay. Now identify lines of forces line by line. And check, does the number of lines of forces entering to the surface is exactly equal to the leaving from the surface? Yes. Yes, see here. This, yes, this is the first line entering, and here it is leaving. Another is entering, again it is leaving. Here it is entering, then it is leaving from the surface. Entering and leaving. Just check, does the lines of forces entering to the surface are exactly equal to leaving from the surface? Yes or no? Exactly. Yes or no? So exactly the lines of forces entering to the surface are equal to the number of lines of forces leaving from the surface. So the net magnetic flux is zero for both the surface. Okay, doesn't matter where, how much the bigger surface or a smaller surface you considering, always the number of magnetic lines of forces entering to the surface is equal to leaving from the surface. Okay, so the net magnetic flux is zero, always zero for all type of surface considered in a magnetic field. This is true for any closed surface, and this is called law of magnetism. And Gauss law of magnetism says for closed surface B equal to 0. Phi B, there is phi electric. Phi E means referring to the electric flux, and phi B refer to the magnetic flux is always equal to 0. Clear? Now, phi E is given by electric flux is given by surface integration. Electric flux is given by surface integration of electric field. This is equals to Q by epsilon naught. Clear? And phi B magnetic flux is given by surface integration of magnetic field B dot ds. Very important. Okay. So this will important for the next chapter, electromagnetic induction also. So phi B equals to B dot ds, and this is equal to 0. Yes. So this is called Gauss law of magnetism. The another one, upper one is called Gauss law for electrostatics, and second one is called Gauss law for magnetism. Clear, beta? So by the Gauss law of magnetism, phi B dot ds equal to 0, or you can say phi B equal to 0. Done, beta? Yes. Noted. Okay, magnetic lines of forces. Once again, I am defining magnetic lines of forces. Magnetic lines of forces are imaginary curve notifying the presence of magnetic field in any given space. Okay, these are closed, continuous, and smooth curve drawn in any magnetic field upon which, important line, upon which a unit north pole can move freely. This is very important. Okay, freely. Actually, the trace out generated by the movement of unit north pole is termed as magnetic lines of forces. So magnetic lines of forces are the imaginary closed smooth curve upon which a unit north pole can move. Look here, this is magnet, and maybe you have performed this experiment in class 10th to drawing a magnetic lines of forces. Your teacher placed a needle here, yes or no? And you show the magnetic north is pointing towards here, yes or no? Okay, okay. So you have seen in that video also key north pole is continuously moving from left end, and the lines of these pointers continuously crowded towards the south pole. Yes or no? So these imaginary curved are called magnetic lines of forces. Okay. So this is only for bar magnet. Inside the magnet, the magnetic lines of forces are from south to north, and outside it is direction north to south. One more important thing, at any point, the direction of magnetic field can be obtained by drawing a tangent. Like if you wish to calculate the direction of magnetic field at this point, just draw the tangent. So in this way, this is your direction of magnetic field. Clear? Where the line of forces are crowded, it means field is stronger, means B is proportional to number of flux per unit area. If the number of flux are larger, then the field will be maximum field will be higher. Clear? And if the flux are rarer, smaller in number, then field will be smaller. That is why near the pole, field are stronger because the number of lines per unit area are stronger. Remember, magnetic field strength is not only depends on phi only, rather they depends on flux per unit area. Okay. Important is how much crowding is there in per unit area. Okay. Independent, not only depend on total flux, rather flux per unit area. Maximum the number of lines of forces per unit area, maximum will be the intensity of magnetic field. Done. So guys, we have completed the first portion of this chapter, that was magnetism. Okay. Now we are moving to the second chapter, that is matter. In matter, we are focusing towards the discussion of magnetic material. What does mean matter? Matter means what matter? Matter means material, and we are going to discuss magnetic material. Well, now we have seen what effect does a magnet creates. Magnet will do this, magnet will do that, like these things. But if you bring a magnetic material inside a magnetic field, then what is the response of this magnetic material for this magnetic field? Okay, so this covers under the study of this material. So topic continues magnetic material. Okay, so in magnetic material, we have to first understood the properties of magnetic properties of material, not properties of magnet, properties of magnetic materials. So there are three types of magnetic material, possibly three types of magnetic materials called paramagnetic, diamagnetic, and ferromagnetic. Okay, purposefully we use in different situation these three type of magnetic materials as per their need. One is called paramagnetic, one is called diamagnetic, another one is called ferromagnetic. The full name is paramagnetic substances, diamagnetic substances, and ferromagnetic substances. Then we see magnetization of these material, how can we magnetize them, and last, effect of temperature on magnetic properties. When we heat these material, when we heat them, materials, paramagnetic, diamagnetic, and ferromagnetic, what is happens, what happening with their properties, and this properties are given by a beautiful law that is called Curie effect, or called Curie's law. Okay. So all these we cover in a coming topic. So start with first important definition to understood the magnetic material, properties of magnetic material. First is magnetic induction. Okay. So write the definition of magnetic induction. Magnetic induction is called B. Magnetic induction is called B. Okay. So first property is magnetic induction. Some theoretical terms are there. So to understand the properties, you should know about these properties. So first is magnetic induction. 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 It is also called magnetic flux density. Magnetic flux density. Okay. So magnetic induction and magnetic flux density is denoted by B. B is equals to number of magnetic flux per unit area. Clear? If you're getting confused with the flux, you can also write phi B or phi magnetic. You also can write it 5 magnetic per unit area because two type of flux are there. So some of you may be confused. One is electric flux. So that's why I using the notation E for electric flux. Okay. And B for magnetic flux. So try to understand what is magnetic induction. The number of magnetic lines of force inside a magnetic substance crossing per unit area normal to their direction is called magnetic induction or magnetic flux density inside a substance. It is denoted by vector B. Clear? You understand this with a beautiful concept like there is a teacher, two teachers are there. Sorry, same teacher is there in the class, and here is a student. Okay, this is a student in two situations. Clear? Now, if teacher giving some lecture in one of the student out of 10, 5 to 6 concept or 9 out of 10 concepts penetrating the student's mind. Okay, he understood what teacher is saying, and in another teacher in another subject only out of 10, 3 lines, 3 magnetic lines substance wise, 3 magnetic lines penetrate this material. Clear? So in one side 9 lines are penetrating perpendicular to this surface, and here 3 magnetic lines of forces are passing through the surface normally. Remember, I using the word normally because when you're talking about the word flux, it should be cross the surface in a direction of 90-degree. Clear, beta? So that is considered only as flux. We have discussed this concept in chapter first, electrostatics, why it is considered normally, why it is taken as normally. Perpendicular direction is important. How? So you've seen there is 9 flux out of 10 and there is 3 flux out of 10. Clear? So which will show the greater magnetic induction? The above one or the below one? You tell me, which will show the great magnetic induction? Which one of the sample, magnetic sample, induced highly? The upper one or the lower one? Surely, upper one. So this sample is magnetized. Magnetic intensity is high because flux number of flux per unit area is same. The area for the both the sample are same. Yes or no? The student is same in both the times, but here only the 3 lines are passing over the surface normally, and here the 9 lines means number of flux in first case are more than second case. Clear? So the magnetic induction for the first sample is higher. So the number of magnetic lines of force inside a magnetic substance, my dear, crossing per unit area normal to the direction, because if you talk about the magnetic flux, it should be passing normal to their direction, normal to the surface, is called magnetic induction or magnetic flux density inside the substance. Clear? It is denoted by B. Now talking about the unit, B is equals to phi by A. Phi is measured in Weber, area is meter square, and Weber per meter square is called Tesla. You must heard about Tesla coil. Okay, Tesla cars. So this is Tesla. SI unit of magnetic induction or magnetic flux density is B. It is Weber per meter square, and CGS unit is Gauss. Remember, 1 Tesla equals to 10,000 Gauss or 10 to the power 4 Gauss. In CGS system, the unit of magnetic magnetic flux induction, magnetic induction is Gauss. Clear? Noted. So, in first definition, you have seen the magnetic induction that in how much extent a magnetic material is magnetized. Okay, so the number of magnetic lines of forces, how much amount of magnetic lines of forces passing through a surface is the indication of its magnetic induction. Now, second is intensity of magnetization. Yes, see, like this is our sample magnetic material. It's not a magnet, it's a magnetic material, simple iron piece. So before magnetizing it, there are molecular magnet, or you can say iron molecules. You can consider iron molecules or iron atoms are arranged like random directions. Clear, beta? So these are the molecular magnets are arranged in simple direction and they having no any dipole. But when you keep a magnetic power like North Pole near them, so if you bring a North Pole near them, then what happens? They will align themselves in a particular direction. Clear? This is what? So zoom this arrow, then this one is the south part of the arrow, molecular magnet, and this is north part of the molecular magnet. Clear? So this whole part becomes south and this whole part become north like this. That's why a magnetic material feeling attraction towards this north part of the magnet. Clear, beta? Okay. So these are the molecular magnets. Now they align themselves. Now they behaving like a magnetic dipole moment. Yes or no? This is capital M. Agree? Traveling from south to north. Clear, beta? So, in what extent magnetic dipolarizes per unit volume? Suppose the volume of the substance is V, this whole volume of this magnetic material is V, and collectively, if amount of material V volume having M magnetic moment, clear? If V volume of material having M magnetic dipole moment, then unit volume having M divided by V. Yes or no? So this is what? This is dipole moment, dipole moment per unit volume. Yes or no? So dipole moment raised per unit volume is called intensity of magnetization. This will reflect in how much extent your material is magnetized. If number of dipole forms are very large, it is called your magnetic material is magnetized heavily. Okay. Large number of dipoles are formed, then magnetic moment will be higher enough. And there are a small number of dipoles are formed only. This is called this material is less magnetized. Clear or not? Like for a same lecture in a class, one student getting very much impressed because he is magnetized completely because his intensity of dipole magnetization is very high. Yes or no? And another student is sleeping. He is taking no interest because only less number of dipole are formed. So its intensity of magnetization is very less. Clear? Here the interaction is very high and here the interaction is very less. Why? Because this is the property of material. This is the property of a matter, substance. This is not the fault of a teacher. Clear? He spread all things equally, but some material take it very well, but some is not taken because its intensity of magnetization is very less. So very few number of dipoles will be formed. So in the same way here, intensity of magnetization, it is defined as the magnetic moment per unit volume. Yes, capital M upon V of the magnetized substance. This basically represent extent to which a substance is magnetized and depends on the nature of the material. It depends student to student. Yes or no? Teacher delivering the same lecture, but some students get very high type of content and some are not interested toward any line. So this is called intensity of magnetization. Clear? Yes, M per unit volume. Right. So if the intensity of magnetization having high value, it means the material is magnetized to a good extent. Okay. So tell me ki what material is said to be a good magnetic material? It should be high intensity of magnetization or less intensity of magnetization. Yes, exactly. Yes. High intensity of magnetization will reflect a good quality of material. Okay, magnetic material. So if magnetization intensity will be high, it means large number of magnetic dipole will be formed inside the magnet. Clear?